In this video, we will be discussing on phenols. We will be targeting the reaction of phenols, the physical properties of phenols, and the effect of the substrate group, that is the OH group, on the position of the incoming group. Before we continue, I would like to appreciate those of you who have taken your time to subscribe to my channel. And for those of you who haven't subscribed to the channel, remember our main goal is to see that you succeed in your exams. But what we want from you is take your time, subscribe to the channel, like our videos, and share to fellow learners who will be writing the exam next year or in 2 years' time. Thank you for taking your time to subscribe to our channel. Let's get started. You know, the benzene ring has 4 positions. It has 4 positions. We have 1, 2, 3, 4, 5, and the 6th position. The second position is ortho. The third position is meta. The fourth position is para. The fifth position is meta. And the 6th position is ortho. But these positions, the 1, 2, 3, the 2, 3, 4, 5, and 6 positions are very, very important in the reaction of benzene compounds. But the elements, the positions, the reaction of this position is being influenced by the substituent group. Should in case the substituent group is X, the substituent group is X, X has a lot of influence in the position of the incoming group. Here we have the different substituent groups. The substituent group, there are some substituent groups that are electron donating, that is, they are ring activating groups, and there are some other groups that are electron withdrawing, that is, ring activating groups. For instance, if X is an alkyl group, if it is an amino group, if it is an OH group, it is electron donating. It is electron donating. Being an electron donating group, they will activate electrophilic attack by directing the incoming group to attack at 2, 4, and the 6 positions. I said if X is an electron donating group, it will direct the incoming group to the 2, the 4, and the 6 positions. And they activate the ring, they activate the benzene ring by increasing the electron density or the negative charges on these positions. When they increase the electron density on the 2nd, on the 4th, or the 6th positions, it helps to activate the ring at these positions. And by doing that, it also activates electrophilic attack at this position because of their electron density at these positions. Remember, alkyl groups are electron donating. When they donate electron to the ring, they have a positive inductive effect. As I earlier mentioned, this will increase the electron density at the second, the fourth, and the sixth position for electrophilic attack. Remember, benzene, one may think that benzene, because it has alternate single and double bonds, it will undergo electrophilic addition. No, as alkenes do. No. Benzene ring is an electron-rich center. It will not undergo addition reaction as alkenes will do. Remember, electrophiles are electron deficient species. They are seeking for centers or areas where there is electron-rich, where there is high density of electrons. So in that case, they will not undergo addition reaction, but they will not undergo electrophilic addition. They will undergo but electrophilic substitution. On the other hand, there are some groups that are electron withdrawing. When they withdraw electrons from the delocalized system or from the benzene ring, they have to deactivate the ring. So these electron withdrawing groups are ring deactivating groups. Examples of these electron withdrawing groups are halogens, the nitro groups, the carboxylic acid group, the ethanol aldehyde groups. These groups are electron withdrawing. Withdrawing. And when they withdraw electrons from the group, they reduce the electron density from the ring. When they reduce the electron density from the ring, then deactivating the ring from undergoing electrophilic attack. And in that case, they are 3 and 5 position directing. They direct this group, they direct the incoming group to the 3rd and the 5th position of the benzene ring. So, for our topic today, phenols. What do you understand by phenols? What are phenols? What are phenols? One may be tempted to think that phenols are like any other alcohol. But that is not the case. We can say phenols are benzene ring. Phenols are benzene compounds with an OH group. These are benzene compounds having an OH group on them. And phenols can be formed. They can be formed from reaction of benzene diazonium salts. By reacting benzene diazonium salt with warm water. Since the diazonium salt is very unstable, if you react benzene diazonium salt with warm water, it will dissociate, releasing phenol, and hydrogen gas will be released. Let me just write how the reaction goes. For instance, here you will see that this is, let me say, this is a benzene diazonium salt. We have this as benzene diazonium salt. we'll have a compound like this. Have a compound like that one. We have yeah, if this one, a hydrogen chloride plus a nitrogen gas that is being released. Let's say this is, remember there is a positive charge here. Warm water. This is a phenol. Benzene diazonium salt. Yeah, in this equation here, you will see the salt, that is benzene diazonium chloride. If it is warm with warm water, because the salt is very, very unstable, it will break down and releasing the nitrogen gas and also forming a phenol. But as I said, benzene should not be considered as an alcohol like other alcohols. It shouldn't be considered as an alcohol as other alcohols. So now, it is different. It is different here because if you look at it critically, as I said, phenol. Phenols are benzene compounds with an OH group on it, on the benzene ring. Then, if you look at the compound of phenol, if you look at the compound of phenol, you will see that in a phenol molecule, one of the lone pairs on the oxygen atom, the oxygen atom of the OH group will overlap. It will overlap with the delocalized system of the benzene ring. It will overlap with the delocalized electron system of the benzene ring. This will increase. It will increase the electron density of the localized electron system. I say when one of the lone pairs of electron on this oxygen of the OH will overlap. It will overlap with the localized electron system of the benzene ring, and this will increase the electron density of the localized or the localized electron system of the ring. And when the electron density of the localized electron system is increased, it makes phenol to be more reactive than benzene itself. It makes phenol to be more reactive than benzene itself. And because of this, it increases the acidity of phenols. So, because of this, it increases the acidities of phenols. Based on this, what what can you deduce as the physical properties of phenol? Based on this, we can deduce that the physical properties of phenols, let me say the boiling point of phenols, the boiling points of phenols, boiling point, the boiling point of phenols, boiling and melting point, melting point, the melting point, and a boiling point. The melting point and boiling point of phenol. If you look critically, you will see that phenol has a higher melting and a boiling point than the methyl benzene. It has a higher melting point than methyl benzene. This is methyl benzene. This is a methyl benzene. And this is and phenol compared. So as I said a phenol has a higher melting point and a boiling point than a methyl benzene. The simple reasons are these. The first reason for this is that the OH group on the phenol can form hydrogen bonds with water molecules. The OH group on the phenol can form hydrogen bonds with the with water molecules. The second reason is that because the benzene ring is non-polar, the non-polar nature of the benzene ring gives benzene or makes benzene to have van der Waals forces, weak van der Waals forces. Then the third reason we can deduce from here is because from this we can deduce, as I earlier said, phenol can form, the OH group on phenol can form hydrogen bonds with water molecules. Then there is the presence of weak van der Waals forces due to the non-polar nature of the benzene ring. This is how the van der Waals forces are formed. You can see it here like this. You have it here. This is a phenol molecule. This is a phenol molecule. We have oxygen here. This is a phenol molecule. We have oxygen here. This is a phenol molecule. Oh, sorry. We have hydrogen here. And this is a phenol molecule. Now Okay, you can now see the formation of hydrogen bonds. Hydrogen bonds are formed between the lone pair of electron on this, oxygen and the hydrogen. They are also formed here between the lone pair of electron, between hydrogen and the lone pair of electron on this other hydrogen and oxygen. It's formed here. It's formed here. You see how the hydrogen bonds are being formed between the lone pair of electron on the oxygen and the hydrogen. So we call these hydrogen bonds. These are all H bonds. These are hydrogen bond formed H bonds. These are all H bond forms between. H bonds that are formed between water molecules and the oxygen on the phenol. So now, that is how they can be formed. Then again, we can go on the acidity of phenol. Phenol is slightly acidic. Acidity of phenol. Phenol is slightly acidic. Acidity. Phenols are slightly acidic. The main reason why phenols are slightly acidic is because the OH group, an acid is a proton donor. It's a proton donor, and it will depend on the ease of that compound to donate the proton. The easier it donates the proton, the easier it donates the proton, the stronger the acidity. So phenol are slightly acidic. Why do I say they are slightly acidic? They are slightly acidic because the OH in the phenol molecule breaks to release the hydrogen ion. The OH on the phenol molecule breaks easily to release the hydrogen ion. So you should see. You will notice that the OH bond break easily because the phenoxide ion that is being formed is stabilized by the partial delocalization of the negative charge over the benzene ring. In other words, I am saying that since the OH group is electron donating. The OH group is electron donating. You will see that when it donates electron into the ring, it activates the ring. The electron, the high density of negative charge on the oxygen goes down into the ring. The strength of the OH, the strength of the between, or the attractive force between the oxygen and the hydrogen on the phenol become weak. And for that reason, it is easier for the OH, it is easier for the hydrogen to break away, to be released as a proton, because all the electrons have been shifted to the ring, the localized electron system. And this can be seen here in this equation here. You will find here that The phenol molecule is phenol and the phenoxide ion. The phenoxide ion that is formed as a result of the release of the proton. Okay, now I said from this equation, I said that the OH bond breaks readily because the phenoxide ion form is stabilized by this partial negative charge over the benzene ring. So you see the conjugate base, this phenoxide ion form as a result of this reaction here. The phenoxide ion formed as a result of this reaction here is the conjugate base. It is stable and less likely to react with the hydrogen ion to give the phenol. This is a conjugate base. What is a conjugate base, or what is remember that every acid has a conjugate. Every acid has a conjugate base and every base has a conjugate acid. The conjugate is that particle that is left. For instance, a conjugate base base is that particle that is left after the acid has donated the proton. So after the phenol has donated the proton, this is the conjugate base. The phenoxide ion is the conjugate base. And because of the stability of the phenoxide, I said this phenoxide is highly stable because of this the partial delocalization of the partial charge, the partial negative charge on the benzene ring. This partial delocalization of the negative charge over the benzene ring gives the phenoxide ion high stability, and for that reason, it is less likely to react with the proton to give the phenol. Let's compare the relative stability. Let's compare the relative stability of the acidity of organic acid with phenol. For instance, let me say ethanol, water, phenol, and ethanoic acid. Let's compare their acidity, the relative stability, the relative acidity of these organic compounds. Let me say water, relative stability, acidity, sorry. Relative acidity. Relative acidity of the relative acidity of some organic compounds. of organic acids. The relative acidity of organic acids. Relative acidity of organic acids. Now you will see that, let's say ethanol. I'm taking ethanol as an example. Ethanol, water, phenol, and ethanoic acid. From here, you will see that ethanol is less acidic. I mean, it's, yeah, and the acidity increases from acidity increases from ethanol to ethanoic acid. There are some basic reasons why the acidity will increase from ethanol There are some basic reasons why the acidity will increase from ethanol to ethanoic acid. From ethanol to ethanoic acid. One, the strength of organic acid depends on the ease at which the hydrogen ion is donated. The ease at which the hydrogen ion is donated. That is the strength of the OH bond. Strength of OH bond. One is strength of the OH bond. Strength. The strength of the OH bond. The strength of the OH bond. 2. The stability of the anion or the conjugate base form. 2. It will also depend on the stability of the anion or conjugate base formed. Stability. The stability of the anion or what we call conjugate base, the anion formed. Another reason will also be on the value of the pKa, because strong acid will have high pKa. The value of pKa. Value of pKa. Strong acid have high pKa. So, once more, as I said the strength of organic acids will depend on the ease at which the hydrogen ion is donated. The ease at which the hydrogen ion is donated. And the ease at which the hydrogen ion is donated, it depends on the strength of the OH bond. Then secondly, Secondly, the stability of the anion, that is the stability of the conjugate base that is formed. And thirdly, the value of the pKa, because strong acids have high pKa. Want to start with um, with ethanol. Let's see with ethanol. With ethanol, you will see that. Let's start with ethanol. Since we said, why is it that ethanol is the weakest? Why is it that ethanol is the weakest? Ethanol, that is CH3, CH3, CH2. Um, in solution, it will give the ectoside ion, that is CH3, CH2, ectoside ion plus the hydronium ion. But it has a pKa of it has a Ka, sorry, Ka of the acid is the Ka of the acid is 10 to the minus 10. Ka is 10 to the minus 18. Mole per dm cube. Welcome back. It should be recalled that I said the strength of organic acid will depend on the ease at which the hydrogen ion is donated. That is the strength of the OH bond. It will also depend on the stability of the anion. That is the conjugate base that is formed. And it will also depend on the value of pKa. Remember, strong acids have high pKa. We want to see, as we're comparing the relative acidity of elements of some compounds, ethanol, water, phenol, and ethanoic acid. We realize that ethanol is the weakest and the ethanoic acid is the strongest. It increases from ethanol to water. The acidity increases from ethanol to water to phenol and to ethanoic acid. We want to see the reason why ethanol is the weakest acid. Ethanol, I said in solution, it forms ethoside ion. In solution, it will form a ethoside ion. It has a Ka of 10 to the minus 10 mole per dm cube. Let's see, since we said on the strength of the OH group O, the ease at which the hydrogen ion is donated. Let's start with the ability to donate the hydrogen ion. The ability of ethanol to donate hydrogen ion. Ability to donate hydrogen ion. You will see that ability ability to donate ability to donate hydrogen ion. You will see that you look at it here, you see here that the ethyl group in ethanol, the ethyl group on ethanol, since it is an alkyl group, the ethyl group is electron donating. The ethyl group is electron donating. And since it is electron donating, it increases the charge density on the oxygen. Since it is electron donating, it increases the charge density on the oxygen of the OH. Then, when it increases the charge density on the oxygen of this OH group, it does what? There is more attraction between the oxygen and the hydrogen. There is more attraction between the oxygen and the hydrogen. So the ability to lose the hydrogen when there is when there is more attraction between the oxygen and the hydrogen of this OH group, on this OH group, there is the ability to lose hydrogen is very, very difficult. The ability to lose hydrogen is very, very difficult. So it is like this. It is like this. You will see it like this. C2 with C2H5, C2H5, it's a partial negative and a partial positive. As I said the ethyl group is electron donating, and when it is since it is electron donating, it increases the charge density on the oxygen of the OH. And if it increases the charge density of the oxygen of the OH, what happens? The ability to lose electron is difficult. Then another factor to see why ethanol is a weak acid. It's the weakest acid. The stability of the conjugate base, that is the ethoside ion that is formed. Stability of the conjugate base. That is stability of the ethoside ion. Conjugate base, call it ethoside ion. Ethoside ion. Okay. It should be noted that that is ethoside ion, that is C5, C2, H5, O minus. It should be noted that the ethyl group increases the negative charge on the ethoside ion. The ethyl group increases the negative charge on the ethoside ion. This makes the ethoside ion more basic than the OH. It makes the ethoside ion more basic than the OH. Why do I say that it makes the ethoside ion more basic than the OH? Because the alkyl group intensifies the negative charge on the oxygen atom and gives the ethoside ion a high ability to accept a proton bases are proton acceptors. So it makes the ethoside ion more basic than the OH. Then let's look for water. Water is another one. Water is water. The acidity of water. You will see here that water water will give the OH of the hydronium ion. Here, with water, you will notice that no electron. Water is has no electron donating group. Water has no electron donating group or electron withdrawing group. For that reason, the ability to donate or to accept the proton is the same. It has no electron donating group. So its ability to accept a proton or to donate a proton remains the same. But it has a Ka of, water has a Ka of 10 to the minus 16. 10 to the minus 16 mole per dm cube. So let's go for phenol. Why phenol has that level of acidity? Phenol. Phenol. C6 H5OH plus water. It will give a phenolzide ion, which is C6H5O minus plus a hydronium ion. It has a Ka of 10 to the minus 10 mole per dm cube. Okay, we want to check the ability of phenol to donate a proton. Ability to donate a proton. Ability of phenol to donate a proton. You should know that, as we earlier mentioned, the OH group is electron donating and is as well ring activating. It is electron donating and ring activating. The lone pair of electron on the oxygen atom becomes part of the benzene ring delocalized electron system. And this decreases the electron density on the oxygen of the OH. And when it decreases the electron density on the oxygen of the OH, the attraction between the hydrogen and the oxygen in phenol decreases. And when that attraction between oxygen and the hydrogen of the phenol decreases, the ease to lose the hydrogen ion is high, and that is what makes a phenol more acidic than the other ones, because it has a very high ability to lose electron. As I earlier said, the OH group is electron donating. they donate electron into the electron benzene electron delocalized system. And when they donate electron to the delocalized electron system, electron move away from the OH group into the ring. And now the charge density within the oxygen has reduced. Now the attraction between the oxygen and the hydrogen has also decreased. And it results in what? It results in the high ability of the hydrogen ion being lost. And that gives phenol, that makes phenol more acidic than other organic compounds. Then let's look also at the stability of the phenoxide ion. That is the conjugate base that is formed when phenol is dissolved in water. There's a phenoxide ion and a hydrogen ion that is produced. Ability of, or the stability of the conjugate base. Stability of the conjugate base of the phenoxide ion. The stability of the conjugate base, that is phenoxide ion, forms. The stability of the conjugate ion formed, or conjugate base formed, that is phenoxide ion. You should notice that you will notice that in a phenoxide ion, the negative charge on the oxygen is delocalized. The negative charge on the oxygen is delocalized around the ring, that is the benzene ring, and reduces the tendency to attract a hydrogen ion. This makes the conjugate base more stable. I said the phenoxide ion has negative charge on the oxygen, and this negative charge reduces the tendency of the phenoxide ion to attract the hydrogen ion, and for that purpose, it makes the conjugate base more stable. The last one is ethanoic acid. Why is it that ethanoic acid is more stable, is more acidic than other organic acid that we just mentioned? Ethanoic acid, why is it different? Ethanoic acid, that is CH3. Ethanoic acid. We want to see why ethanoic acid. From the equation, you will see it. Why ethanoic acid is more acidic than other acids that we just mentioned. You will get it from here. You will see that from here you can see from this reaction ethanoic acid in water, to give ethanoate and the hydronium ion, you will see that this acid is between ethanol, water, phenol, and ethanoic acid. Ethanoic acid is the strongest among all these. The reason is because of its high stability, the high stability of the ethanoate ion. The high stability of the ethanoate ion. And the high stability of ethanoate ion is as a result of the negative charge that is spread throughout the COO group, the COO minus group. The negative charge is spread out, and it's that negative charge that gives ethanoate the stability. It is that negative charge that gives ethanoate the stability. A recap. I said that phenols, from the onset I said a phenol compound, this is a compound that has a phenol. These are benzene compounds. They are benzene compound with an OH group on them. And I went further to give you how phenols are being produced. Phenols are produced from benzene diazonium salt. For instance, benzene diazonium chloride. This salt is very, very unstable, and if heated with warm water, it decomposes. It dissociates to give the phenol and the nitrogen gas that is being released. Then, because of the nature of phenol, phenol has some physical and chemical properties. And some of the physical properties which I said was the boiling point and the melting point. The boiling point and the melting point, I said that phenol have high melting and boiling point than methyl benzene. They have high melting point than methyl benzene. And the reason I gave there was that phenol can form hydrogen bonds with water molecules. I said phenol can form hydrogen bonds with water molecules. That was the reason I gave. I went further for the acidity, for the chemical property of phenol. I said phenol is slightly acidic. Why is it that phenol is slightly acidic? It is slightly acidic because since the OH group is electron donating, when it donates electron, it increases the electron density or the charge density in the benzene ring. And for that reason, it decreases the attraction between the oxygen and the hydrogen of the phenol. And when this decreases the attraction between the OH group, what happens? The ease to lose the hydrogen ion is high. And when it loses the hydrogen ion, that gives phenol that ability of being acidic. I went further again to compare the relative acidity of some organic compounds. I gave an example of ethanol, water, phenol, and ethanoic acid. And I realized, on comparing them, we saw that ethanol is less acidic than water. Water is less acidic than phenol, and phenol is less acidic than ethanoic acid. The acidity increases from ethanol, which is the weakest, to ethanoic acid, which is the strongest acid. And in that case, I said the acidity of this compound will depend on three points. And the first point is the strength of the OH bond. That is the ease at which the hydrogen ion is donated. Another one is the stability of the anion. That is the conjugate base that is formed. And the other one is the value of the pKa, because strong acids, they have high pKa. We started with ethanol, and we said that ethanol is very weak. It's very weak, and we gave the reason that it is as a result of, because the ethyl group, because it is CH3, CH2OH, the ethyl group is an alkyl group. It is electron donating. And when it donates electron when it donates electron to the hydrogen that is attached to the oxygen that is attached to the hydrogen, it makes the electron density or the negative charge density on the oxygen high, and that gives oxygen and hydrogen a strong attraction, and that makes ability to lose the hydrogen on the hydrogen of the OH difficult, and that makes ethanol a weak acid. We went further to water, and we said that with water, we said that water has no, it has no electron donating group, it has no electron withdrawing group. So that ability to accept a proton, that ability to lose a proton is the same. So in that case, no influence on it. We went further to phenol. We went to phenol. Looking at phenol in water, it gives a phenoxide ion, which is the conjugate, and the hydronium ion. And we saw that for phenol, the OH group again on phenol is electron donating, and it is ring activating. So the lone pair of electron on the oxygen atom becomes part of the benzene ring delocalized electron system, and this decreases the electron density on the oxygen of the OH. And when it decreases the electron density on the oxygen of the OH, the attractive force, or the force of attraction between the oxygen and the hydrogen of the OH decreases. And when that force decreases, that gives the ability for the OH to lose the hydrogen easily. And that makes phenol slightly acidic more than the other ones. And lastly, we ended with ethanoic acid. That ethanoic acid is the strongest among all. So I gave an equation of ethanoic acid in water to give ethanoate and the hydronium ion. And I said this one will depend on the stability of the ethanoate that is being formed. And the stability of this is as a result of what? It's as a result of the negative charge that is being spread out through the COO minus group. That gives ethanoic acid, that makes ethanoic acid the strongest acid among this group of organic compounds. Then we will be visiting the reaction of phenol with metal. The reaction of phenol with metal. For example, reaction of phenol with sodium metal. And the reagent in this situation is, the reagent here is sodium metal. The condition is at room temperature. But the product of it is an acosite and a hydrogen gas that is being produced. Acosites are these we call them acosite because the hydrogen of the OH is being replaced by a metal. The hydrogen of the OH is being replaced by a metal. That's why we call them acosite. So the reaction here is when a phenol reacts with sodium metal, this is what you will see. Phenol phenol plus sodium. Phenol plus sodium, you will see an acosite is being formed. An acosite. An acosite is being formed, and hydrogen which is also released. A hydrogen is also released in this case. A hydrogen is also released in this case. So this is this product form here is what we call sodium phenoxide. Sodium phenoxide. This is an alkoxide. This is an alkoxide. I said it's an alkoxide because the hydrogen of the OH group is being replaced by a metal, then with a hydrogen gas. Hydrogen gas. Hydrogen gas. That is what is being produced. Then the second reaction will be between sodium hydroxide. The second reaction will be between sodium hydroxide. Between sodium hydroxide, we will have between sodium hydroxide we will have the reagent is sodium hydroxide solution. The condition is still room temperature, and the product is alkoxide and water. Phenol, we have phenol. We have phenol plus sodium hydroxide. Phenol plus sodium hydroxide will give us, sodium phenoxide. It will give us sodium phenoxide plus water. Sodium phenoxide plus water. We say it is sodium phenoxide plus water. Sodium phenoxide, and this is water that is being formed. And the last reaction for this group, is a reaction with halogen. A reaction with halogen. A reaction with halogen. That is halogenation. You will see that phenol will be this phenol on this plus phenol here plus bromine. Let me take bromine here. As I said, phenol, the OH group is electron donating, and it is 2, 4, and 6 directing. It is ring activating. It activates the ring at the 2nd, the 4th, and the 6th position. So if it reacts with any halogen, you would be phenol will not react. Phenol will not react with in the presence of UV light with any halogen, or with a halogen carrier like aluminum chloride or iron 3 chloride, which will help to catalyze the reaction. They will not do it. They will not need a UV light. They will not need any halogen carrier to catalyze the reaction. The reason is simple. This is because phenol is very, very reactive. From the onset, I told you phenol is more reactive than benzene, than the benzene ring. So in that case, they can react without a halogen carrier or without UV light when they are reacting with halogens. So that's why the reagent is only chlorine or bromine at room temperature without a halogen carrier or without using UV light. And since they are 2, 4, 6 directing, what they are going to produce will be 2, 4, 6 tribromophenol. They are going to produce 2, 4, 6 tribromophenol. And bromine. Bromine is a reddish brown liquid that will decolorize this solution. So we will have 2, 4, and 6 tribromophenol. That will be our product. If we're using chlorine, it should be remembered that if we're using another chlorine, it will be 2, 4, 6 trichlorophenol. If you are using iodine, it will be 2, 4, 6 triiodophenol. So we can generally say it is 2, 4, 6 trihalophenol. So this will be our product. We will have bromine here, and bromine here, plus 3 hydrogen bromide. Say the name of our compound will be 2, 4, 6 tribromophenol. So if we was in the lab and you were given phenol and phenol under room temperature to react with bromine liquid, what you will observe, your observation will be, there will be a reddish brown color of bromine. So there will be a reddish brown color of this substance. There will also be a white precipitate that is formed. There will be also a white precipitate that is formed at the position formed as a result of the 2, 4, 6 tribromophenol. Based on the product that are also produced, there will also be a steaming fume of hydrogen bromide that will be observed. I said there will be a steaming fume of hydrogen bromide that will be observed. A white precipitate will be formed, and this white precipitate is the 2, 4, 6 tribromophenol, and there is the reddish brown color of the bromine that is being decolorized. The reddish brown nature of the bromine will be decolorized. So this is what I have. Then finally, we will be going to alkylation, reaction with alkyl benzene. Our next topic will be reaction of alkyl benzene. So thank you for watching. Once more, I want to thank those who have taken their time to subscribe to this channel. And for those of you who haven't subscribed to the channel, please, as I earlier said, Remember that our goal is that you succeed in your exams. But if you haven't subscribed, please take your time, like our videos, share to prospective students who will be writing maybe next year or in 2 years' time. And most importantly, subscribe to this channel. Thank you. Wishing you best of luck in your exams.